This is our problem 5 in the same block of problems on work and work energy theorem. And this problem will be with vertical springs. Always fun. What this problem is about? I have an ideal spring. Ideal spring, this is unstretched length of this ideal spring. And I choose my origin, y0, to be at the position of natural spring length. Then I know that force of this spring is described by Hooke's law that tells me that force of the spring is minus spring constant and then deviation from equilibrium, which is y minus y naught. But in my case, y naught is 0 because I decided to go with y0 at the unstretched position. Okay, so then I put the box, I attach, this is an important word, I attach a block of mass m to this spring, and this spring now is compressed by some amount, and they gives us this amount. This amount of compression is 0.1 meters of the natural length of the spring. It's definitely not up to scale. So this is 0.1 meter from the unstretched position. I definitely exaggerated this compression. So it is compressed by amount A, and since it is compressed, it is below 0, y is equal to minus A at this point. And then I let it go. And the question is, how high will this spring go? So what will be my final position of this spring? I neglect the size of this block. So what will be my final position of the spring when this block stops at the highest point? So I'm giving the constant, spring constant. I'm giving this amount of compression. I'm given mass of this block, and I need to find what will be the highest point, y sub s, with respect to y0 when the block stops. Which law will we use to solve this problem? Let's think about it. I know something about the initial velocity of this block. It starts from rest. I let it go. I know something about the final position of the block. It stops there, so I know something about the velocities. I know something about the displacement. I know the forces. What will be the forces, spring and gravity, acting on this block? Why don't we use the work energy theorem to solve this problem? What is work energy theorem? Work done by the net force is integral from R1 to R2 F net dot dr. And now we will apply it to this problem. Is it work energy theorem? No! This is work done by the net force, and it is equal to the change in the kinetic energy, mv2 squared over 2 minus mv1 squared over 2. And now this is correct. Let's just apply work energy theorem to solve this problem. v1 is 0 because we just let it go. Initial velocity is 0. v2 is 0. Why? Because this block stops there. Oh, look at this. We are making progress. The right-hand side of this equation is 0. Now we need to write left-hand side of this equation. So what are the forces acting on this object? There is force of gravity vertically down, and there is force of spring when this object is in this position. So I will do this. Force of spring. Spring, I will just put S. Bringing this block, acting up. Okay? So work done by this net force will be equal to the integral. Now, I write this formula. I write F in terms of components. There is no X component of this force. I just write Fy dy from our formula that we derived before. Let me write it. So it will be Fy dy from y1 to y2. It's independent on x. The question is, what is fy? mg comes with minus. Or let's write limits first. Where do we start? At minus a. I will write all formulas in symbolic form, and then at the very end we will plug in the numbers. So we start at minus a. How high do we go? To ys. Okay? Then fy net. Here, this is important. Net. What is it? Gravity down, minus mg. Projection of gravity on y is negative. What about force of spring? Positive or negative? Look at this formula. It is always minus ky if we put our origin at the unstretched position of spring. Minus ky dy. Let's look at it one more time. Why is there minus? I just applied Hooke's law. Here is minus. I put here minus ky, but does it right? It is up. However, it is up, but y here in this region is negative. So negative y, negative is positive. And yes, in this region we have force of spring acting up. Our formula takes care of all these situations. Now, when the object is above zero, what will happen? Now, force of spring will be acting down, trying to bring it back to this equilibrium. Y is now positive, minus from formula positive y. Yes, again it is correct. Minus ky works again. So, we have minus mg, minus ky here. And why do I use the same limits? Because both of these forces are acting from minus a to ys, since the block is attached to the spring. All right, and what is the right-hand side of this equation? We are not done. We did not put the right-hand side of the equation. It is equal to 0. Oh, look at this. This is the equation that we need to solve to find ys, the highest point. And it looks like we have one equation and one unknown variable. Let's see if we can solve it. I take this integral right here, minus mgy. Are you with me? You can pause the video, do it yourself, and then we will compare our results. Who knows? Probably I'll make a mistake. Minus ky squared over 2. And the limits are from minus a to ys. And this is equal to 0. Now I plug in the limits. Upper limit gives me minus mg. And then I have in parentheses, let me think. Let's do it in parentheses. Now I have ys minus lower limit and minus. So ys plus a here. And then I have minus k over 2. And then here I have ys squared minus lower limit minus a squared gives me a squared. This is minus a squared, and minus from the lower limit. Wonderful. And this is equal to 0. We don't have to get the right-hand side of the equation. Looks complicated, but it is not. Let's do this. Let's rewrite this guy as ys minus a times ys plus a. So you know that this could be done minus mg ys plus a. I leave this guy minus k over 2. And then I'll rewrite this one as ys minus a times ys plus a. These two are identical, and this is equal to 0. What I'll do next, I will factor out this guy. I will have ys plus a, and then in parentheses, I will have minus mg minus k over 2 ys minus A. And this is, oh, I need to close the parenthesis. And this is equal to 0. So the first root that we have here, ys plus a equal to 0, ys is equal to minus a, that's where the block starts. We are not interested in this root. Let's look at the second root. What do we have here? We have mg minus k over 2, ys minus a. And this is equal, this has to be equal to 0. Now, I will change probably minus to pluses. We multiply by minus 1. And now we need to solve for ys. What is ys? Ys is equal to, I have a that comes to the another side of the equation, a. And then I have minus mg divided by k over 2. K and 2 comes here. I try to make it good looking. So one more time, a comes to another side of the equation. So it is a, and this comes with minus. So it is minus 2mg over k. Now let's see if it makes sense to us. Imagine that there is no gravity, just no gravity. Then it is from minus a to a, makes sense. But since there is gravity, it has to stop at the, yeah, the scale is far from what it should be. It has to stop at ys that is less than a, because it is a minus 2mg over k. This picture is definitely not up to the scale. Let's correct it. So what I want, obviously, ys has to be smaller than a. It is a minus something. So we will stop right here, somewhere here. This picture is not up to the scale still, but now looks better to me. So a minus this. And now let's plug in the numbers. What are our numbers? They give us a as 0.1 minus 2 times m, which is 0.05 kilograms. And then we have g, which is 9.8 meters per second squared. And I divide it by k, which is 25 newtons per meter. Well, we can simplify it a little bit, 0.05 here, 25 here, but I did my homework. And I calculated this number. And if you calculate this number, it will come as 0.061 meters. So we found ys, the highest point reached by this spring above level 0. Problem solved. Just one more time the strategy. We knew something about the position of the object. We knew something about forces, and we were looking for the highest point. We found work done by the net force and put it equal to the change in kinetic energy. The object started from rest. This is highest point. It stops there. So the right-hand side was 0. Then we wrote the projections of both forces in y. We took this integral and we solved for ys, the highest point.